Thank you for coming. Thank you for coming. My name's Eddie Barron, and I've been at PSI for about a year and a half.
Wow.
And uh, so I want to actually tell you about work that I've done in collaboration with my graduate student, Anthony Burrow. And it's two papers. They're both published. And in fact, Anthony is going to defend his PhD thesis in a little under 3 weeks. Um, the focus is trying to understand type 1a supernova. As you know, type 1a supernova are important because they are very, very bright. So you can see them out to cosmological distances, and they're standardizable candles, so you can use them as cosmological probes. And of course, they were used to discover the dark energy, which led to the 2011 Nobel Prize. But we still, I mean, there's still, it's not like cosmology is completely solved. And so we still want to, and of course, there's this thing called the Hubble tension. So we still want to improve type 1a as cosmological probes. And where we're at now is that they're statistics limited. So we're not going to improve their accuracy by just getting more of them. 1 over root n won't do it. And so we have to improve our understanding of them. And coming, or already started, with Euclid, but then coming in the next few years, we're going to start observing them at higher redshifts with Roman and Rubin, as well as Euclid, of course. And so we really want to, get prepared for that. Embarrassingly, we don't know a lot about what a type 1a supernova is. We all agree that the star that explodes is a carbon-oxygen white dwarf in a binary system. More than that, we really can't say. What the companion star is it an ordinary star? Is it another white dwarf? We don't agree. What the explosion mechanism is, we don't agree. So we really need to try to get an understanding of what the progenitor system is and how it explodes. And since they're transient events, we get what we get. We may get an optical spectra at a certain time and then a near-infrared spectra at a different epoch. We may get photometry in one band at a certain time and another band at a certain time. So it would be really nice if we could develop machine learning that, given a subset of data, could sort of extend and predict the rest of the data, particularly fill in missing data as a function of time evolution. And the other thing that, in order to use type 1a supernova as cosmological probes, that is to determine, what their intrinsic brightness is, we have to have K corrections. And so that means we need the SED. So so that's sort of the motivation for this work. So the general spectrum of a type 1a supernova is shown here. And what makes it a type 1a supernova is this feature right here, this silicon 6355 line. Although, to be honest, the real unique thing is this sulfur W here. That's actually the thing that's only seen in type 1a supernova. The other thing I want to point out is because these are explosions, it's an expanding atmosphere, the profiles of lines have this P Cygni shape with this blue shifted absorption and then this rest frame emission. So it's this double shape. And when I talk about velocities, the velocity of, say, when I talk about the velocity of the silicon 6355 feature, what I'm talking about is actually what wavelength is this minimum of the absorption of the blue shifted absorption at, and then, the Doppler formula gives me a velocity for that. I'm going to talk about this diagram developed in almost 20 years ago, so-called branch diagram. And what it is it's a plot of the pseudo-equivalent width of these two features, these two silicon features. So this silicon 6355 feature and this silicon 5972 feature. And note it's a pseudo-equivalent width because there's no well-defined continuum in a type 1a spectrum. And in fact, if we go back here, you can see that, in fact, this is our machine learning program. It doesn't do a great job on this because, you know, if I was putting the continuum here, I would move that up. So that's the problem with these pseudo-equivalent widths, is that they're not that well defined. So if we can replace them, that's something useful. So here's a modern branch diagram. This is from a paper just published a month ago. You can see they're color-coded here, that there's 4 different groups. That's what the branch diagram does. It takes this plot of these two pseudo-equivalent widths on the x-axis and on the y-axis and breaks the supernova up into these 4 groups. These guys down here are called shallow silicon. They're intrinsically bright. These guys in the middle are the core normals. Those are the ones you really want to use for cosmology. These guys up here are cool. They're intrinsically dim. And these guys over here are broad lines, and there's not much I can tell you about them because they're not well studied. And you know, yeah, I've color coded it, and particularly on this diagram, you know, if I hadn't color coded it, it's like you may say, well, groups? What do you mean groups? It just sort of looks like a continuum to me. So I mean, that was one of the goals of this machine learning, was to, are there really groups? Can we quantify the groups? So what do we need for the input? So the machine learning inputs for the branch diagram was developing a good Gaussian process regression tool, which gives us consistent smoothing of the spectra, because obviously different spectra, you know, we take what we get. Different spectra have different levels of signal to noise, different wavelength coverage. So consistent smoothing of spectra, and then an interpolation function so that we can do integration to get the pseudo-equivalent widths. And then for the group membership, we use Gaussian mixture models, which gives quantitative measurements of the probability of group membership. And in order to determine the number of groups, we used the delta BIC, which is the Bayesian information criterion, as well as the silhouette score. And that comes out with 4. It really does come out solidly with 4 groups. So this is what we get. And this is from Anthony's paper in 2020. So you can see that we, you know, these are contours. We really do get 4 groups. And the color coding represents the probability of group membership. So yeah, there's really solidly shallow silicons, there's really solidly core normals, but then there's a transition region where, you know, some of the circles are brown. They're not, you know, they're not red, they're brown because there's some mixture. And some of the diamonds are brown, they're not blue because, again, there's a mixture. And that happens into the broad lines as well. And specifically, you know, we can tell you exactly what the percentage, what the probability of each membership, of each group membership is. So that's, I mean, that's a big thing, you know. It's 14 years, or yeah, 14 years later, these groups are first really put on a solid framework, and there really are groups. It's not just a continuum, there really are groups. So the next order of business is dealing with the SED. That's particularly important for K corrections and also for determining bolometric light curves. So our goal in that project was to take an optical spectrum and then be able to predict the infrared spectrum or the near infrared spectrum. So we do have a relatively uniform sample where we have both optical and near-infrared spectra. We have to do this as a function of time because the supernova evolves. So this really has to be a function of time. But the sample size is small. I mean, it's tens. It's 25. So we can't use machine learning things that require enormous sample sizes. You know, galaxy SEDs are predicted using autoencoders, but they have sample sizes of like 1 million. And here we have sample sizes of 10. So the thing that we decided on was principal component analysis because it works well for small samples. And then we wanted to be able to weight, for example, the noisy telluric regions. So we chose a specific incarnation expectation maximum PCAs or EMPCA. Here's our results. Obviously we had a training set, and then this is the validation set. So these supernova were not included in the training. And in fact, it was hard to find this validation set because it sort of was hard to find supernova that had both simultaneous or near simultaneous optical and near infrared spectra at decent signal to noise and at the time that we wanted them. And, you know, what's nice, so what we did is these two dashed lines show the region that we used for prediction. So it's roughly from 0.5 to 0.85 microns. And then to the right of that, so redward of that, so that's the input spectrum, and then to the redward of that is the predicted spectrum. And in the black is these are, we have these, you know, this is validation, so we actually have observed near infrared spectra. And you can see that it's decent. Again, it gives us an error snake, so we know, you know, what the uncertainties are. And, you know, like I say, the predictions are pretty decent. And looking here, and also sort of interesting is these two. So 11FE is not a pure core normal. It's actually only 74% core normal. And this one, 21 AEFX, is, you know, less than 60% core normal. So it's, you know, these aren't the cleanest supernova that we could have given our machinery, but yet we get decent results out. And another nice thing is the predictions capture many of the correlations between these are known correlations between near infrared features and branch diagram type. So that's a nice again result or validation. Using the fact that, you know, the branch diagram seems to be important, so we tried that again, but all we did was move what we feed into the machinery. So we give it only a much smaller bit of optical spectrum, so only from about 0.5 to about 0.7 microns, and then out comes these results. And again, they're not bad. So this is again sort of telling us that, boy, that silicon region, there's something there, you know, there's something there that is really predictive of the SED of these supernova. Here, this is not a great one, and this is sort of interesting. 2014J is a very nearby, well-observed type 1A, but it's sort of an odd one. It's a core normal, but the velocities are high. And actually, I neglected to mention, in our training set, we had absolutely zero broad lines. That's the way it came. We had no broad lines. And so, this offset, the features aren't actually bad. It's just that the flux jumps up there and sort of stays up there. So then there's some other interesting machine learning findings. So this is not a branch diagram. This is a plot of absolute magnitude, so intrinsic brightness. So here, all the supernova in the sample, their light curves have been fit, and their intrinsic brightness has been determined, versus that silicon 6355 velocity. And you sort of see that, as I said, the core normals really are the ones you want to use for cosmology. They have the smallest spread in intrinsic brightness. And the shallow silicons are the bright ones, and the cools are the dim ones. You see that. But you also see this tail of the core normals into the broad lines. And in fact, you see, core normals well into the broad lines and even into the outliers of the broad lines. So there's something going on with high velocity supernova. And we see it here as well. This is from our PCA analysis. So this is the PCs plotted against different pseudo-equivalent widths. So PC2 correlates actually quite well with 5972, and that's maybe a great thing because, as I said, the pseudo-equivalent width is this not very well-defined quantity, whereas the PCs are quite well-defined. So maybe that's a good thing. Maybe we can get rid of the pseudo-equivalent widths. And we see PC3 correlates well with the other pseudo-equivalent width, except for these high velocity ones. And I don't know how well you can see it, but they're color-coded. So these up here are high velocity core normals. These over here are high velocity broad lines. And you can see that they're just sort of outliers. So there's something going on with high velocity supernova. So this works. These machine learning techniques work. I mean, the first thing is that they really have quantified these branch groups, which have been going on for a long time. And we're sure they really exist. It's not just a continuum. There really are groups. But also, this now gives us access to predict SEDs. And of course, we did it from optical to near infrared. Obviously, the next thing to do is go from optical to UV, and write an HST proposal to do that soon. And this will lead to, like I said, better K corrections, better bolometric light curves. And then, since we're so ignorant about what the progenitor system is, what the explosion mechanism is, we're really always looking for these clues. So there is a clue that something is really up with these high velocities. We don't know what yet, but it points us to further research. So thanks, and I'll take questions.
I have a question about what do you mean with K correction?
I have a backup slide for that.
Because is it
okay? So when we observe an object at high redshift, obviously the SED is redshifted. So when we go do photometry, so here is the same supernova, actually just redshifted. So the blue line is rest frame, and the orange line is redshifted, observed at a redshift of 0.2. So obviously, if I take the U band flux or the B band flux, I'm going to get different answers. And the K correction is just, what do I need to do to get the same answer? So,
and that's how is that determined? Empirically or?
It's done usually with models of what the SED are.
Oh, okay. All right.
And
Thanks.
that's why we need the SED for, as we go to higher redshifts, we need more and more of the SED in order to make these K corrections, and they're important.
So I got a real bone, basic question, and that is, these supernova explosions are used as measuring distances or measuring age or something, or I guess it's the same thing, distance and age. But is it just based on the spectral shift, or something to do with their absolute magnitude?
It's their absolute magnitudes. It's that you can, from the photometry, from measuring the light curve as a function of time, you can again make this empirical. Now it's purely empirical correction in order to determine their absolute magnitudes. And obviously, once you know their absolute magnitude, from their apparent magnitude, you can get the distance module if you get the distance.
Right, but are all these things have the same absolute magnitude?
No, they're correctable. I mean, you measure the shape of the light curve, and then from the shape of the light curve, there's an empirical relationship which tells you how to correct it. Is it slightly dimmer or slightly brighter than the mean, or and so it gives you a formula of how to correct and determine the intrinsic absolute magnitude.
Okay. Sounds like a lot of data to figure out.
It's a lot of data. I mean, it's again, I emphasize that these are empirical relations, but they're on reasonably sound theoretical footings, given the fact that we don't understand the whole thing, right? I mean, and so, improving putting the empirical relations on a sounder theoretical footing is very important if we're really gonna, if people are really gonna believe that, is the Hubble tension real? I mean,
and these SN1 explosions, are they all a mass accretion on a white dwarf from a
yeah, from something, from something. That's the question: is what's the something? Is it another white dwarf? Is it, and that's where we don't agree. I mean, my suspicion is that it's from more than one thing, but there's probably a dominant companion.
So would so like Cygnus X1 has a black hole going around a blue giant, and so but to get to a black hole, there's probably been a supernova explosion somewhere in that history, right?
Yeah, but that's probably a real supernova explosion, a massive star. So probably that's a massive star exploded, either made a neutron star that then accreted material and turned into a black hole, or just the explosion wasn't successful and material fell back and made a black hole directly. But it is less likely that was this thermonuclear explosion. The other thing is that these type 1As are, they're 1/5 of the total supernova. They're only 20%. The rest of them are from core collapse supernova, because core collapse supernova is like, you get a massive star, let it live its life, it's going to make a core collapse supernova. So
makes a statement on the way out. Yeah. Okay. Great.
All right. Well, thank you all for listening.
Thank you, Eddie. Pleasure.
Bye.